Hi, in this video, we wanted to take a look at spatial point pattern analysis. Okay, so everything I've done for spatial statistics so far has been like make a map, make a visualization. Huge important aspect of spatial statistics. Now, if you think about all the material that you learn in a statistics course, visualization is not the be-all, end-all. Even though it drives a lot of our conclusions, a lot of our decisions, we actually, as statisticians, as data scientists, we start pulling in mathematical structure to make decisions. Now, if I do a visualization and I see something very extreme, I can reach a conclusion without doing actual statistics. But it's in that gray area where it's a maybe, maybe not. Where's the cutoff? I don't know. That's when the power of being a statistician really kicks in. So what we do, we take the data we have, we incorporate some mathematical theory, and then we're able to get a result. All right, so the first thing we're going to do, we're going to just do an introduction and look at some easy peasy aspects of working with spatial point pattern analysis. All right, so in this, you're going to see PPP. That stands for point pattern planner or planner point pattern. Either way, it doesn't matter how you want to say it. And that is an object in the stat package, a class for how our data will be stored. All right, so I'm going to be working through an example for applied spatial data analysis with R. The example I'm working on is from the textbook's website. This is part of chapter 7, and we're going to look at subsections 7.1, 7.2. All right. Here are the data sets you need if you're going to run this at home. All right, so introduction. A point process is a stochastic process. So when I say stochastic, I mean that there is a random aspect to it. So when I say random, I'm saying like the mathematical sense of random, in which we observe the locations of some events of interest within a bounded region. The bounded region is going to be important for what we do because that's going to impact our probability distributions. The locations of the events generated by a point process in the area of study will be called a point pattern. All right, so let's talk about 7.2, packages for analyzing spatial point patterns. All right, so how I'm going to go about this is I'm going to jump into an example, dive in, get in on it, start working on it. All right, so what I'm going to do, I'm going to load the Japanese pines point pattern data sets. All right, the data gives the location of saplings of Japanese black pines in a square sampling region in a natural forest. Okay. Now, we're going to be using the stat package. So it's for spatial statistics. And this, if you look through the internet, you look through documentations, you look through books, you'll see that this package is the heavy hitter for point pattern analysis. The data set that we're working with is actually not from SpatStat, but from spatstat.data. And we'll also be using spatstat.geom for some features. And we can see that there's quite a few packages that come along with this. All right, so let's load the data. So I'm going to use the data function to load it. It's in the spatstat.data subpackage, Japanese pines. All right, now what I get back is a data set with 65 points on the unit square. Okay, so something that's going on with this is that the actual area of observations where the observations were recorded were converted over to the unit square. The reason for that is to make the mathematics of the analysis easier to work with. Now here in this situation, 1 unit corresponds to 5.7 meters. So that tells me that we had a square region that was being evaluated, and that square was just rescaled to 0, 1. All right, so let's just go ahead and plot it, just so I can get a feel for where things are distributed. All right, not too shabby. Okay, so now let's look at the summary statistics of this point pattern in the plane. And notice that the 0, 1 by 0, 1 is we're doing that conversion, that transformation is to make our mathematics easier when we start doing the pencil and paper aspects of statistics. So we've got it. So if I go ahead, I take the data set, I pass it to the summary function, which is in the SpatStat geom package, then I'll get this information. So we can see that, 65 points per square unit. 1 unit is 5.7 meters like before. The coordinates were given to 2 decimal places. And, so we've covered pretty much everything about that. All right, so now something I would like to do is to be able to invoke other packages. So what I want to do, I want to take my point pattern data set and convert it to spatial points. That way I can go ahead and invoke other packages throughout R. All right, so how we're going to go about doing this is that I'm going to take the as function. I'm going to pass the object is my point pattern. I'm going to say the class is spatial points. And then I'm going to grab the summary statistics. And so now you'll notice that I have a square, but that's no longer 0, 1. So there's a bit of a conversion that R saw that it was 5.7 per unit and went ahead and changed it to the 5.7 by 5.7 meters squared. Okay, and we don't have any information about the projection, so it just says projected is NA. All right, so what I'm going to do, I'm going to take the map tools elude function to translate my spatial points I have up here back to the unit square. That way, I have it on the unit square as spatial points in the SP package. So that way I have it on the unit square and it's in a format I can use with other packages very easily. All right, so I'm using map tools. Here's the function I use. I tell it the object I want. I say I do want to rescale this, and I want this to be on the unit square. And then boom, with the summary from the SP package, I can see that it correctly converted to the format I want. And I still have the 65 data points that I started out with. All right, so now everything is looking pretty good. But you know what? I want to be able to go from spatial points to planar point patterns. So I want to show you how do we do that? How is it that we can go back and forth? Well, once again, I'm going to use the as function, AS. This is a base R function. I specify the object. I specify the class, just a standard way in R to do this. And boom, we can see with the summary function, still got 65 points. And we can see that, decimals, we're given 2 decimal places, and we're on the unit square. All right, all right. All right, so now let's pull in another data set. So I'm going to pull in the California Redwoods point pattern. Now this is the entire data set. Help documentation talks about different aspects and some things that are going on with this data. I just chopped it down to this little blurb that if you use question mark Redwoods full while you have SpatStat loaded, that help documentation will come right up. All right, so the data set is Redwood full, and it's in the SpatStat.data package. And here I'm going to convert it over to spatial points. Now this is the author's code, and I believe that everything works the way we want to when we load this. I don't think we have to do any conversions. Now let's do biological cells point pattern. All right, so here the data records the locations of the center of 42 biological cells observed under optical microscopy in a histological section. The microscope field of view has been rescaled to the unit square. All right, so you notice that I'm making sure that I have everything on in the same region and in the same, so for these studies, same region, same bounded area. That way everything is going to make sense when I start doing my hypothesis testing. So I use the data function to load it. It's the cells data set in the spatstat.data package. And then once again, like I've done so many times before, I convert this over to a spatial point using the as function. Easy peasy lemon squeezy. Now, everything's great, everything's wonderful with this, but I've got 3 separate data sets floating around. I would like to put this into one. That way, when I do my visualizations, I can just boom, drop one data set into the function and plot everything all at once. So what I'm going to do, I'm going to row bind the 3 data sets. So we're going to use the rbind function in R. Now, I like rbind for one particular feature of it. In general, I hate this function. This function can cause problems. It's slow, but it's nice in that it doesn't get picky about column names. If you work with tidyr's bind rows, that function does the same thing. It's faster. It's generally accepted as the better version of row binding, but I can tell you from experience, it's very picky about column names, which can kind of be a pain in the neck. So rbind doesn't give me this headache. And so here I went ahead and used rbind on this. All right, so what I do, I go ahead and I convert each of my 3 data sets to coordinates, because that's what they are. And then I put them into row bind, so they're stacked on top of each other. So the first rows are the Japanese pines, then the redwoods, then the cells. Go ahead and record the number of rows corresponding to each data set. And now I add on a column. This is not the most elegant way to do it. There have been a few slicker ways to go about it, but this is definitely functional. I go ahead and I tack on a new column that indicates where did I get my data before I did the row binding. And then I set up the names of my columns. The tidyverse would have made me specify the names of the columns, each data set, before I could do the row binding, which can be, I mean, you can do it, it's just kind of tedious. All right, so now let's go ahead and visualize the spatial points. Let's use the lattice package. We're going to use the XY plot. What this does for each variable that we have for the data set origin, it's going to make a subplot. That way I can see what's going on. Okay, and so here I can see that cells, I mean, that's pretty evenly distributed. I can see that there's some like clumping up on redwoods, and the Japanese look like it's somewhere in between. All right, so now let's do another example of working with point pattern data. What I'm going to do, I'm going to go through, I'm going to read several data sets that are relating to asthma and pollution. So for this study, they have the location of children with asthma. They have some control subjects. They have location of sources of asthma, and they have a bounded region. Now, what's really important about this example is that this is a non-standard boundary for what's going on. And since it's a non-standard boundary, it'll be a little bit more interesting for the mathematical hypothesis testing I'll do in an upcoming video. All right, so here I've got the asthma data set in a shape file. Here, this is the boundary. I'm reading these with the RGDAL package, read OGR. The DSN is my file path. The layer is just specified as what it is. And strings as factors equals true is how the author set this up. And then the rest is very similar. Here's a source of pollution. and then we have roads. All right, so when I take a look at this, I can see that I have 1,291 features and 9 fields for this asthma data sets. So I think it's a spatial points data frame, if I remember correctly. Then for the boundary, we have 1 feature and 1 field. I believe this is a polygon. Then for source, we have 3 features, 1 field. And for roads, we have, there's just 1 layer and 1 feature, 1 field. So now let's go ahead and visualize this. All right, so what we're going to do to visualize this is I'm going to put down an aspect, and then on top of that, I'm going to stack some more data, which may possibly overlap with the visualization I put down before. The one that is last is the one that will be on top, it's the one that will be visible. So here I'm putting down the boundary first. So if there's any overlap, I know the boundary will be plotted below the others. Then I'm plotting roads. Now we're putting down asthma. And here we're worrying about, is this a case or a control? So here, this will be for the case, and this will be for the control. Now we're applying down the source, and you'll notice that that's going to be brown. And here I've got my legend saying what's up. Now notice that here the point background is blank when I'm talking about the source. That'll be apparent why that is. And when it comes to the others, I can see that I've got these colors here. And notice that for the source, I've got black and brown. Well, I have single colors, medium, aquamarine, and goldenrod. And we can see that it's going to be control, cases, pollution, sources. So controls will be medium, aquamarine, cases will be goldenrod. Pollution sources are going to be black with a point background color of brown. So let's take a look. And so there we go. Now that is a very irregular shape in terms of sampling for spatial statistics, but that's what we've got. And by having a very precise area for our spatial statistics, I'll be able to get a stronger inference. All right, well, that's all I've got for you. Take care and goodbye.